Welcome to day 3. We're going to look at half-life and doubling time. How can we rewrite exponential functions using a little bit different formula. So our basic formula is still y equals a times b to the x. A is the initial amount. B is the change factor. So this inside the parentheses is the b value. But r is a rate, some percent. So r is equal to the percent divided by 100. So if p of t is an exponential decreasing function, and it has to be decreasing, what is the usual name for the number t that solves the equation that gives me p of t equals half of some initial value, or gives me half of some other value? Well, this is the whole idea of what we call the half-life. The half-life is the amount of time it takes to have half of some previous amount. If I have 10 and then later I have 5, I want to know how long it took me to go from 10 to 5. Okay, let's try it on this graph. This is an exponential decreasing function. Well, this value here is 10. So 1, 2, 3, 4, 5 is half. I'm going to try to draw this best I can. Horizontal. Let's see. 1, 2, 3, 4, 5, 6. If I do this correctly, you could see this is 6. So for y equals 10 to y equals 5, which is half the value, this half-life is t is equal to 6. Let's try another example. Well, if I make this 4 and I make half-life as 2, well, this comes out to here, and of course I'm just doing it as best I can, eyeballing it. This comes out to here, and I notice from here to here this is still t equals 6. So from y equals 4 to y equals 2, I still have a half-life is still t equals 6. So if I read this problem, I see the half-life of this substance is 5 years, and originally there's 1,000 grams, so I could just write it like this to begin with. 1/2 to this x, where this stands for the number of half-life cycles. So my question is, how much remains after 15 years? Well, 15 years divided by 5 gives me 3 half-life cycles. So I'm going to plug 3 in here. And when I put this into my calculator, well, I could do a 3 half times. Half of 1,000 once is 500, twice is 250. A third time would be 125 grams. So after 15 years I would have 125 grams. Well, now I'm going to rewrite it by incorporating this 5 years into the formula by using this little bit change. Instead of a times b to the x or a times b to the t, it's a times b to the t over k. T is still t, but k is the unit time for one change to occur. So how long it takes for a half-life, how long it takes to do a doubling time, or whatever you say is going on. So I can rewrite this formula as r of t is equal to 1,000. I still have 1,000. A half is still my multiplier, and I'm going to do t over 5. I'm going to incorporate that 5, the half-life cycle, into the equation. So now when I figure out how much I have after 15 years, I'm going to use t equals 15, and I get r of 15 is equal to 1,000, 1/2, 15 over 5, which, if I have a newer calculator, I don't have to worry so much, but if I have an older calculator, I have to do this first, and I can rewrite it as r of 15 equals 1,000, 1/2 to the third, which is exactly what I had before. I have 125 grams, exactly what I had before. To show you in the calculator what I mean, this is a newer calculator, so 1,000, parentheses, a half, raised to, and you notice when I do a raised to, I get this little shadow box. If you get this little shadow box, I could just do 15 divided by 5 right in that shadow box, and I don't have to worry about the fractions. If I didn't get that shadow box, I would have to put parentheses around all fractions. So by using this new formula where I have that 5 in the denominator of the exponent, I don't have to worry about how many half-life cycles I have. I can always figure that out, but it's just a lot easier not to do it, and this is actually more precise. So I've set up my two problems, how much I have left after 50 years or how much I have left after 77 years. I'll go to my calculator and figure that out. So typing this into the calculator, obviously a calculator handles this very well. And my rule of thumb for all these problems is I should always round to 3 decimal places. If I don't tell you, the standard is 3 decimal places. And I'm going to put these back on the paper. And you can see I have my results here on the paper. 50 years, I have a little bit less than a gram. And after 77 years, I have a very small amount, 0.023 grams. So now I'm going to do, how do I find how long it takes to get to a certain amount? So this is where I use my graphing calculator again. I'm going to take my formula of y1 equals 1/2 x over 5, and y2 is equal to 100. And I think by now we should know that we're looking at a graph that looks like something like this. One is exponential decay. One is just going to be a horizontal line. And we're trying to find where they intersect. And I'm going to go do this on the calculator. Okay, here I am on my calculator. I'm going to put in 1,000. And it's up to you. If you want to use 0.5 for a half, use 0.5 or 0.5 for a half for the same thing. If you want to use that fraction, you could do 1/2. Or you could use a special fraction key by hitting this alpha key and the y equals. You could get 1/2. It's not that important for this problem, but I like showing it because it's useful in other things we do. X over 5. That's my exponential function, and I want to see when it equals 100. And again, I never hit graph, I choose a window. So I'm going to choose a window. 0 through 20. Well, let's see. After I'm going to get down to 100. 20 may be enough. Let me put it up to 50, just in case. I could always make it smaller. I don't need 12,000 as my max. I'm going to make it 1,000. That was the initial value. Maybe even that's too big, but that's okay. I hit graph, and I can see where the exponential decrease is the blue, and the horizontal line is the red. Again, we do second trace, number 5, first curve, second curve, my guess, it doesn't matter. And I get an intersection of about 16.6 years. And there we have it. I have my intersection of 16.610 years. Now for the second problem, I'm going to do the same thing. I'm going to keep my y1 the same. And this time I'm going to make my y2 equal to 10. Okay. So again, we're going to get the same looking graph. Exponential decay, and then a horizontal line graph. But this number is much smaller So I might change my window on this. And this is what I mean by changing my window. So I'm going to go to my calculator, go to my y equals. I'm going to change the second one to only 10. And I'm going to hit graph to see what happens, to see if it's a good window. And I could see it. Now, I don't like that. I mean, I could. It's still going to do the intersection, but I don't really like that I can't see it. I don't think I need my y max to be 1,000. I don't have to see the whole top of the graph. Let's say I make my y max 100. Okay. I don't have to see the whole exponential function. I just got to see where they intersect. So you can see I can't see the top of the blue graph, but it doesn't really matter. I see a better intersection of the red and the blue. Second trace, number 5, enter, enter, enter. And I'd see the intersection, and it probably would have worked the other way, but I do like seeing it more clear. And you can see for the next one, I got an intersection of about a little bit more than 33 years. Okay, so how can we write different models depending on what we have? So basically, I'm making a joke here. We live in an ocean of air. We do. And air pressure varies differently based on altitude. For each increase in 1 mile, we lose 20%. Well, losing would be 1 minus 20%, which would be my 0.8. At sea level, or the initial value, I have 14.7, so when I use miles, m of x is equal to 14.7, 0.8 raised to the x. This x stands for miles. Well, if I want to convert it to how air pressure changes per foot, I have to convert miles into feet by 14.7.8 x over 5280. Now, this x value stands for how many feet I have. So if you wanted to go to Everest, Everest is pretty high up there, 29,141, 14.7.8, 29,141 over 5280, and we get Everest is about 4.290 pounds per square inch pressure. That's not a lot of air pressure. If we're normally used to about 15, this is less than a third. That's why people need to bring oxygen with them. It's very thin up there. And if I do it for the Dead Sea, which is below sea level, so it's of negative 1,300 feet, is 14.7.8 to the negative 1,300, 5280, we get 15.530 pounds per square inch. And that's a slight increase of what we're used to. So we don't really feel much of an effect if you go down to the Dead Sea. Up at Everest, you would feel the effects. Okay, so we're trying to figure out what annual interest we have if it takes 7 years to go from $10,000 to $20,000. Well, maybe the one thing I should do is write things as ordered pairs. Time is the input, and my money is my output. 7 years later, I have 20,000. And I'm trying to find the annual rate of interest, and I know it's an exponential type of problem, so I'm using y equals a times b to the x. I know my initial value is 10,000, so I have y is equal to 10,000 b to the x. I don't know what my b value is, and that's what I'm trying to figure out. So I'm going to use this second order pair. 20,000 is equal to 10,000 b to the 7th. Divide by 10,000. I get 2 is equal to b to the 7th. And to get rid of the 7th power, I take the 7th root. I get b is about 1.104. Okay. That's my multiplier. It's growing. I'm going to subtract 1 from it. So I get R is equal to 0.104. I change that into percent, and I says grows by 10.4% per year. So if it takes 10 years or 7 years to double your money, you're growing by a little bit more than 10% per year. So the whole idea is that how do I change? How do I go from this modified equation where I have the built-in time frame into a regular equation? Okay, because I could have rewrote this equation above as y equals 10,000 2 to the x over 7. It takes 7 years to double in value. Well, this new equation would be y equals 10,000, and it would be 1.104 to the x. These two are the same equation. One is in the special form. It says times 2 or double every 7 years, and this one says grow by 10.4% per year. You get the same result. So the idea is that to change this b value to the t over k into this regular b to the t, I'm just going to use t equals 1. So I do b to the 1 over k, whatever the k value is. You have to know the k value, and that's your new b value, the b value that you want. Essentially, you're doing the kth root of b. And that's what I did in this example over here. I said double every 7 years, and I took the 7th root of 2 to get this number of, well, first I got this number of 1.104. That's my b value, and I figured out my rate. And that's what we're working on. How do we translate things into that special form, raised to the t over k, to the regular form, which is a b value? I went back to this air pressure problem just to show you what I mean. I could take the 5,280th root of 0.8, and I get this really decimal number with a bunch of 9s in it. And I could rewrite the problem. So let's just show you that for every foot, because x is in feet, for every foot you go higher, you lose, the difference in air pressure is inconsequential. It only matters when you go up to Mount Everest at almost 30,000 feet. So I'm going to show you 2 ways to do a problem like this. You have 10 bacteria doubling every 3 hours. B of t is equal to 10, 2 for doubling, t over 3. Or the other way we can do it is use the idea that I could do 2 to the 1/3, and I put that in the calculator, and I get 1.260. That's a rounded number. That's not exact. So when I see this number, I see that it is growing by 26% per hour. But then I can rewrite this problem as b of t equals 10, 1.260 raised to the t, and they both are basically the same type of problem. Okay, one says, the red one says doubling every 3 hours, and the other one says growing by 26% per hour. They essentially mean the same thing. The one in blue is a little bit off because there's a rounding off of that decimal number. So when I have to do my 12 hours, b of 12 will be 10, 2 to the 12 over 3, and you can go to a calculator and you get 160 bacteria. And when you do the same thing over here, I'll choose black, b of 12, 10 times 1.260 raised to the 12. You're going to get a decimal number on your calculator, but because this is bacteria, it's like population, you only can have whole numbers. We get that. when I go to 20 hours, b of 20, I get 10, 2 to the 20th over 3, and I get 1,016 bacteria. And when I do it over here, b of 20 is 10 to the 1.260 to the 20th. I get 1,017 bacteria when I go to my calculator and round it off. And you say, why is it different? Well, because 1.260 was a rounded off number, there is a round off error here. Very small. A difference of 1 in 1,016 or 17 bacteria is inconsequential. That's less than 0.1%. So now I want to see when there's a million bacteria. So I'm going to use my graphing calculator. I'm going to put these two equations into the calculator. You know they're going to look like this: an exponential growth and a horizontal line for the million. I go to my calculator, go to my y equals. I'm going to clear everything out. And it's 10 parentheses 2 raised to the x over 3, and then a million. Now I better choose a window, and I'm thinking, I don't know if 50 is going to be enough. It's going to be close. I'm going to go to 100. My y max has to be more than a million. Now let's just make it 2 million. Makes my life easy. I graph my exponential and my horizontal line. They do intersect. It's close to the middle. So I'm going to trace number 5. Enter, enter, enter. And I get a little bit less than 50 years. So I get x is equal to 49.829 years is when they intersect. Now, I'm going to do the same thing, but with the blue equation where it was rounded off a little bit. So I set up the blue. You see, here's my equation. It's going to be the same looking graph. I'm going to go to my graphing calculator, and I'm going to change my y1 to be 1.260 raised to just the x. Oops, I got to go over and delete a couple things. There we go. And the graph's going to be very similar. I mean, you can't even tell the difference between the two graphs. The blue graphs look exactly the same. Second trace, number 5, enter, enter, enter. And we get slightly a different result than before. Inconsequential. Very, very small difference between the two of them. And if I said years before, I meant hours, and you can see there's a very small difference between the amount of hours it takes to get to a million. Very, very small difference. Okay, let's write a model for a function for country A. Well, the population of A is going to be 25,000, doubling every 50 years, t over 50. Now, I could also convert this and do 2 to the 1 over 50th power, which I get about 1.014. That is a rounded off number, but I could rewrite this as a of x is equal to 25,000, 1.014 to the x, and since it's bigger than 1, if you subtract 1 from this, I get 0.014. That means it does grow by 1.4% per year. Doubling every 50 years is growing by 1.4% per year. These two, the pink and the green, are basically the same model, but the pink is better. It is an exact model. For country B, I can do, well, I have 100,000. And it's just decaying by 2.1%. Well, let's see. 2.1% is 0.021. 1 minus that is 0.979. 0.979 to the t is the model for the country B. I'm going to use this one for country A. It is the better model. And then the question at the end is, when are they equal to each other? So y1 is equal to 25, 2 to the t over 50, and y2 is going to be 100.979 to the x. I should make them both x, because that's what I can type in my calculator, x. Notice I can get rid of the thousands in both. You know, as long as it's, if I did 25,000, 100,000, or 25 on 100, you're going to get the same thing. The pink is going to start at 25 and grow, 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 grow. The blue is going to start at 100 and decay. So we're going to go find this intersection. So here are my two models, my y1, my y2. I'm going to hit my window. I could probably leave that as 100 years. Maybe it's too big, but I could always make it smaller later. That 2 million is way too big. Remember, I got rid of the 1,000, so I'm just going to make it 100. That we'll see both graphs. There's a growth, there's a decay. Second trace, number 5. Enter, enter, enter. And you get a little bit less than 40 years. So this intersection right here is that x equals 39.511 years.